Hello. So we will wait for 2 more minutes and then I will start. So hello everyone. Welcome to the live session. I will introduce myself. I am Anjali Negi, currently pursuing PhD in IIT Kanpur. So this live session is about to solve GATE previous year problems, where you can actually find the GATE portal in Google and then you can follow the previous year solved problem from there for any particular subject. So yes, I will start the session. Hello everyone. In this video I will be solving GATE 2015 chemistry question number 46. This question states that the distance between two successive planes in a simple cubic lattice with lattice parameter A is. We are given with 4 options. So before starting, let's discuss some basic.
So the mathematical description of a plane and a normal vector and a normal vector. So for example, if you look on your right, so this is x, y, and z axis, and here if the intercept of a plane that is shown in blue color is a, b, and c respectively, then this plane has an equation as shown here, x by a plus y by b plus z by c equal to 1. Okay, And in a case where any of these three intercept, that is A, B, and C, these are any of these is equal to infinity. For example, if the intercept A is equal to infinity, that means that the plane never intercept intersect the x-axis. Okay, and then the equation will become y by b plus z by c equal to 1. This is the equation of the given plane. Now, if A, B both become infinity, then the equation of the plane is just x z by c equal to 1, or we can write it as z equal to c. So this particular plane I have shown here in red. So this is the only intercept with the z-axis of this plane, and so this is the plane. Also, for every plane, there is a unique normal vector for every plane. For example, in the plane in blue, this plane has a one unique normal vector that is shown in and having a direction, that is n vector. And also for this plane in red, we have vector in k direction, that is here because if you this is the equation of the normal vector, that is n vector is proportional to I unit vector upon A plus j unit vector upon B plus k unit vector upon C. So this is the equation of the normal for each plane. Okay, so if this normal is for, I am describing it for the plane which has only intercept at z direction, then A and B become infinite, that is this and this portion becomes 0. So only k by c will remain. So that is why it's in the direction of having a direction k unit vector. Okay. Now the unit length, when we find the when we remove this proportionality and we find the unit length, so so it get the whole equation of the normal vector get divided by the length of the vector. So this is how we find the unit length. So this will become 1 upon a square plus 1 upon b square plus 1 upon c square in a square root will divide the equation of the normal vector. Now coming to the concept of parallel lattice planes. So if you assume here, this is a one-dimensional lattice point arranged in a lattice. So this is a one-dimensional lattice plane. Okay. Now, if this is the axis in blue, okay, say A and B, and again in red, say again A and B. So in blue, if we see that there is a plane passing through these two atoms, okay. So these two atoms, so blue plane passes through them. So it will cut the axis in A and B in some point. And again, if there is a similar plane parallel to it, passing through another two atoms in a similar manner, such that these two planes are parallel to each other. Here, actually, the lines are not straight. So, but assume they are straight planes and they are parallel to each other. So then we get a series of parallel planes, and these are called the family of parallel planes. And we have a special notation for these parallel planes. We call it as Miller indices. Okay, so this is what we have. Now coming to the concept of Miller indices for lattice planes. So assume that lattice translational vector, that is the A, B and C vector, are perpendicular to each other. For example, in this figure, you can see that A, B and C are perpendicular to each other. So the first step is to look for lattice plane closest to origin, and that plane should not be passing through origin. If it is, then we can take another successive plane which is parallel to it. For example, here this is the plane in blue shaded in green. So this plane intercept axis A. Okay, you can extend it axis A, axis B, and axis C such that it intercepted in 1, 3, 2. Okay. So if I write intercept at A first, that will be A, 2, 1. Okay. So this is the intercept for the A, B, and C vector. Okay. Now the next step is to take the reciprocal and multiply by the least common multiple. So we will take the reciprocal of each intercept and multiply by the common multiple. That is, here it is 6. So we'll multiply it by 6. So the Miller indices, the notation is such that it is notated in square brackets. So it is 2, 3, 6 in square bracket. So this is the Miller index of that particular plane. So now the case is if the intercept is negative, so use bar. For example, -2 can be written as 2 bar. Okay. Now the Miller indices for the direction. So in square bracket, I can just denote for making it simplify and generalize HKL as 2, 3, 6 here is HKL. Okay. So this in square bracket gives me the direction, and if it is in normal bracket, then it will be a plane or a surface. Then in square bracket for 2, 3, 6, this is the actual direction, that is the 2a vector, 3b vectors plus 6c vector. Okay, under root divided by the length of the given plane or vector. So it will be 2 square plus 3 square plus 6 square. Okay, taking the square root. Now coming to the cubic system. So if I have moved from one dimensional lattice plane to a cubic system, which is 3D. So here we have again same type of arrangement, three axis A, B, and C. And these are the lattice point in 3-dimensional. I tried to make it. Then in our question, we were asked about the distance between two successive planes. So there are two planes, so both have the same direction or plane or surface, that is 110, 110, in a simple cubic lattice with lattice parameter A. So the lattice parameter is A, and I have only shown, for example, 1101 plane here. There will be another plane successive to it, that is parallel to it. So yes, to find the distance between these two planes, we need to apply this formula, that is the distance between two planes DHKL is equal to A is my lattice parameter divided by h square plus k square plus L square, that is my Miller indices. Now my D110, this distance between these two planes will become A upon under the root 1 square plus 1 square, that is root 2. So the distance between two successive plane 110 in a simple cubic lattice is equal to A upon under the root square root 2. Okay. So the correct option for this question, the distance between two successive plane in a simple cubic lattice with lattice parameter A, is option number D, A upon under the root 2. I will highly recommend you to go through the NPTEL reference, Miller Planes, Miller Indices by Professor Madhav Ranganathan, Department of Chemistry, IIT Kanpur. I am attaching the link below. Thank you.
Yes, so if you guys have any doubt, you can type. So if not, I will move to another problem. So the next one is also related a little bit to this one, but it's a different problem. So that's why I showed you first the concept of Miller indices. Now we will move to a concept called Bragg's law. Okay.
Hello everyone. In this video we will be solving GATE 2012 chemistry question number 36. This question states that for a face-centered cubic lattice, the Miller indices for the first Bragg's peak, that is the smallest Bragg angle, are. So let's move into some basic, then we will try to solve the problem. So what is Bragg's law? The structure of crystals and molecules are often being identified using X-ray diffraction studies, which are explained by Bragg's law. Correct? And so let's look into the given figure here. So this figure shows some layer of the given crystal or solid. So say this is layer 1, layer 2, and then layer 3 with a spacing of D, which we can actually denote as D. For the first Bragg's peak, that is the. So what is Bragg's law? The structure of crystals and molecules are often being identified using X-ray diffraction studies, which are explained by Bragg's law. Correct? And so let's look into the given figure here. So this figure shows some layer of the given crystal or solid. So say this is layer 1, layer 2, and then layer 3 with a spacing of D, which we can actually denote as DHKL, where my HKL are the Miller indices. Okay, and the black dot refer to the atoms spaced in that particular layer of the crystal or given molecule. So when the ray, that is X-ray here, is actually incident on the given crystal, like for example the ray 1, the X-ray 1, when incident, and if it strike say atom X here, then it will get reflects, and the theta angle is the angle of reflection. Okay, so this is theta here and this is theta here. But if somehow it misses some atom in the layer 1, it then goes in the depth of the layer, that is in the up to layer 2 for example, and then get reflected from atom Y, such that there will be two conditions now. So the two conditions are that it either it will go and makes constructive interference. So how can I show? Yes. So either it can just say this was my ray 1, and from ray 2, say I am making we are having a constructive interference. So if I am having a constructive interference, I will get some peaks, which are refers to as Bragg's peak. Okay. But in the case where this reflection of ray 2 is not following any condition of constructive interference. However, it is following the condition of destructive interference, let's say. Then the given output will have no peaks, and hence we do not detect any Bragg's peak there. But so, what are the actual condition for this to get the constructive interference? So that is what the Bragg's law is. So the path difference that you will see between ray 1 and ray 2 is yx. The distance yx is the path difference, and that is also twice. Okay. So the 2yx is the path difference between ray 1 and ray 2, and it can be expressed as equal to 2d sine theta in terms of sine angle. If you will find out by putting some normal and then calculate the in terms of 2yx distance as 2d sine theta. So if the path difference is equal to an integer multiple of the wavelength, so the wavelength of the light or the X-ray that we are using, if the path difference, that is this, is equal to the integer multiple of the wavelength, then the ray 1 and ray 2 will arrive at atom X, for example here, in the same phase, okay, and hence we will get a constructive interference. And the condition that explained here, we can write it in the equation form, that is the integer multiple of the wavelength and lambda is equal to the path difference, that is 2d sine theta, and this is what we call as Bragg's law. Okay, yeah. So the families of planes have the same atomic arrangements and are denoted by HKL. So these are the Miller indices that we talked in the problem given, that is the planes that we are given. For example, here plane 1, plane 2, plane 3. So these are the family of planes and they have same atomic arrangement in layer 1, layer 2, layer 3, and hence they are denoted as HKL, where my HKL are the actual Miller indices of each plane. So to calculate the interplanar spacing, that is the DHKL between any two plane, in a cubic system we have the formula like this. So this is the extra details that we actually don't need, but you have to keep this in mind whenever we are talking about the interplanar this spacing. Okay, so in a cubic system you can actually calculate the interplanar distance spacing, that is 1 upon d square. So this is the square of d HKL is equal to h square k square l square, the summation 1 upon a square, where my a is the lattice parameter, correct? So in a cubic system you will have a as a length, breadth and height, correct? And so note here is that, so here is the catch. So the Bragg's law is necessary for diffraction, but does not guarantee it. So this is the Bragg's law that we have seen is actually necessary for the diffraction to occur, but it doesn't guarantee that it will give us a constructive interference. So this is for unit cell, that is a cubic unit cell, but for other atoms, when we go to the other atoms, the reason is that the phase center, body center, or etc. Atoms that are present, they can also produce some out of phase destructive interference. So in such cases, no, it is not a guarantee, even if it follows the Bragg's law, okay, that we will get the constructive interference. So that is not a guarantee in the case of FCC or BCC unit cells, okay. So the catch is here that the trick is that the BCC or FCC unit cell will give us the Bragg's peak when the Miller indices in BCC is actually the sum of H, K, and L is equal to the even number. And in FCC, we will see that the HKL, that is the Miller indices, are either all even or all odd. Okay. So yes, so let's move into our problem that was given. So for a phase center cubic unit cell, so we are given with FCC. So the Miller indices for first Bragg's peak, so R. So to get the Bragg's peak, we know that our HKL either all even or all odd, correct? Yes. So the given option that we have among the four A, B, C, D, the one which satisfies this condition to get the Bragg's peak is option number B. Okay, because it has all 1, 1, 1, that is all odd. Yes, and here we have odd, even, okay, and B is the one which is having all odd option. So option number B is correct. So I will refer you to go through NPTEL reference, Bragg's law in reciprocal lattice and origin of systematic absences by Professor Anshuman Roy Chaudhary. Chemical Sciences, ISA Mohali. Here is the link below. Thank you. Number B is correct.
So anyone have doubts? So actually I have a question for you guys that since before this we have seen one video for Miller indices. So as I am talking about that FCC unit cell should have either all even or all odd Miller indices for to have to show Bragg's peak. So my question is that whether option A, C, and D. Uh, yeah. So my question is that whether A, C, and D will belong to FCC or not. Anyone can comment. You can type also if you don't want to unmute. Okay, so A will belong, yeah. Anyone else? So, do you want to comment how you are saying that A will be? Uh, yes, yes. Yeah, actually, when I made this video, after that only I was thinking that the other options have even and other that Sambhav Mitro is saying 0 is even, 2 is even. That's correct. So actually, what I was thinking that to approach this problem, you can just help me also that to approach this particular problem, where they are asking me to find out the Miller indices for the first Bragg's peak. That means n is equal to 1, correct? And my lambda is something which I don't know. If I consider say X-ray, then I can say a range of 0.01 to 10 nanometer, I think, and then 2D sine theta. So for smallest Bragg angle, so the theta should be smallest. So either I can calculate D using all the four option, because I have shown you uh, D, how to calculate D using Miller indices, but again I don't have A. So all of you who are present here, you can also comment. I personally have not found any other solution to this particular problem. So I so any of you who want to comment or suggest something, or have already solved this one? Okay, so no one is saying something. Anyway, so I will look into it again, but Sambhav, do you have anything to say? How to approach this problem in other way? Swabhav. Okay. You guys can type also if you don't want to unmute. Okay. Pushpita? So let's all take this as a homework or whatever. Y- yeah, Pushpita, I know. Actually, that's why I'm doing this discussion with all of you. You all are from different background, having MSc from different institute, and might have covered this topic or not. That's why I wanted to know whether some of you or any one of you have solved this problem or have any idea, because when I was solving I got this approach only and I made the video, but I am also not sure about it. That's why I'm discussing with all of you. So Swabhav, do you have any idea or have any approach to solve this if you got this in the gate exam, say? Yeah, if actually I said in the video that it's odd, but when I searched that it's even. So I am also not sure whether this how they are saying this. But okay, so let's take all of us take this particular problem from gate 2012, question number 36. You can note down, and hopefully if I get any particular solid answer for this problem, I will discuss in the next live session, or any of you will get, then we will you can remind me. I will definitely will discuss this, so you can also search. Okay, so I will move into another. So someone has just joined. So Kedar, if you don't mind, then we have a problem in our hand. So this is from gate 2012, question number 36. So uh, yeah, so if you have solved this problem earlier, you can join in the discussion and tell us like how to approach this one. Actually, what Swabhav Mitro, you have said all are even, hence FCC, but I will look into it, because according to me it should be only this case that the option A, C, and D should not be satisfying the Miller indices for any FCC unit cell, and that's why we can neglect all the three option, and B will remain. So for 1 1 1, yes. So I will. Okay, so let's move into another problem. So don't worry.
Hello everyone. In this video I will be solving GATE 2012 2012 chemistry question number 18. This question states that the number of terminal carbonyl groups present in Fe2CO9 complex is. So let's move into some basics. So this diiron non-carbonyl Fe2CO9, which we can also write the IUPAC name as trimucarbonyl bis tricarbonyl iron. Here we have to note that the IUPAC name itself is giving described that the mu is described as a bridging carbon. So there are that is the three carbonyls are acting as a bridging carbon between the two metals Fe. Also that Fe is in a having the charge 0, that is why it is written as iron, and it is a orange solid, and it is more reactive source of Fe0. Here, if you look into the structure given, yes, then these two metals, iron as a Fe, then you can see that the three bridging carbonyls CO in 3D, you can see that one lie on the plane and other two are above or below the plane. Okay, and the other six carbon, the remaining six carbon are actually the terminal carbon where three carbonyl are attached to one metal each. Okay, so this is the structure, and from here we can get that the question that we were asked, that the number of terminal carbonyl groups. So the terminal carbonyl groups that you can see here are actually 6 in total present in the given complex is. So our correct option is C, 6. So I will refer you to go through the reference of application of carbonyl metalates by Professor Prasenjit Ghosh, Department of Chemistry, IIT Bombay. Here is the link below. Thank you.
I hope there is no doubt in the given problem. So let's move into another.
Hello everyone. In this video, I will be solving GATE 2018 Chemistry question number 48. This question states that in a molecule XY, let psi x and psi y denote the normalized atomic orbital of atoms x and y respectively. A normalized molecular orbital of xy is given by this expression. The value of the overlap integral of psi x and psi y is. So, before solving for this expression, let's get familiar with what are the atomic and what are the molecular orbitals. So we are given atomic orbitals. So we are given the atomic orbitals of our molecule X and Y, and psi X and psi Y are respectively the atomic orbital of X and Y atoms. So the molecular orbital is a linear combination of atomic orbital. So we can actually call it as LCAO molecular orbital. So the linear combination of atomic orbital can be written as psi plus minus C1 psi x plus minus C2 psi x. Now this is a general expression. Here this psi plus is my bonding molecular orbital, and this bonding molecular orbital is written as C psi x plus psi y. To find the normalization expression for this psi plus, we have to put psi plus in the normalization condition. So the expression for normalization is the integral over whole volume space. So psi x conjugate is multiplied with psi x, or actually I can write it here as psi plus conjugate with psi plus equal to 1. So when I put psi plus expression into this, I will get c square integral dr. So psi x conjugate plus psi y conjugate multiplied with psi x plus psi y equal to 1. Now when we solve this, we get 4 different integral. So here this 4 different integral get further simplified when we apply the normalization condition. So again this first integral and this third integral are equal to 1 because of the normalization condition, and this second and the last expression is equal to s. This s is actually the overlap integral, capital S, which is the overlap between the two atomic orbitals, so that is x and y. So we can so this expression psi x conjugate psi y and psi y conjugate psi x is equal to capital S. So we get c square 1 plus s plus 1. C square is common. So on solving this, we get c is equal to 1 upon under the root 2 multiplied with bracket 1 plus capital S. So here we know that our normalized expression for, so this is my normalized molecular orbital. So actually this is a bonding molecular orbital. So my normalized bonding molecular orbital will be psi plus equal to, where this was earlier C. So I have replaced the expression for C with 1 upon under the root 2 into 1 plus S. So this is my overlap integral. So S is, so yeah. So we have to find S here. So in our question, we have to find, we are given with the expression psi plus is equal to 0.56 multiplied by psi x plus psi y. So when we compare these two expressions, we know that 0.56 is equal to 1 upon under the root 2 1 plus s. Here we have to find the overlap integral, and overlap integral is capital S. So we have to find s here. So this will be, after solving, s equal to 0.59. So the answer for this is, the value of the overlap integral is 0.59. I will highly recommend you to go through the lecture number 61, Molecular Orbital Theory for H2 plus ion. This given by Professor Anindya Datta, Department of Chemistry, IIT Bombay. This is the link. Thank you.
So you guys have any doubt? Okay. So I will move to the last problem.
Hello everyone. In this video, I will be solving GATE 2012 Chemistry question number 47. This question states that the number of possible isomers for the square planar mononuclear complex, the given complex of a metal M is. So we have to find out the number of possible isomers. So yes, so isomers are molecules with the same molecular formula but different arrangements of atom. So we are given with that it is a square planar complex. So this is my complex with a mononuclear metal M. So this metal M at the center, and since it's a square planar, I have drawn one square around it, and hence you can actually see that we have, for example, ammonia, okay, and CN, or I can have ammonia and CN. Okay, so we have a total of two isomers. So the number of possible isomers for these are actually uh, either in a cis or a trans condition. So when we have same kind of ligand at one side, we call it as a cis, and when we have same ligand at opposite of the diagonal, then we call it as trans. Okay. Yes, so the number of possible isomers for the square planar mononuclear complex of metal M is, the correct option is option number A, but I have to mention here that in 2012 GATE paper, the question number 47, the answer is marks to all. Okay, so yes, for this particular problem, you can check the NPTEL reference Isomerism 1 by Professor Debashish Ray, Department of Chemistry, IIT Kharagpur. Here is the link below. Thank you.
Yes, so if you guys have any doubt or if you have any feedback to give, so your feedback is welcome. I will again mention for those who have joined the meeting late that you guys can check out all the video solution in Gate portal. You can search Gate portal in Google and then you will be directed towards the site, and choosing any particular subject you can choose either year wise of or topic wise. You can have the video solution ready which are uploaded in the site. Okay, so you can check out there also. So previously also we have done the live session of 12 week where video solutions were made for gate previous year questions, so you can check out that in that site by choosing the topic or year. So guys, have any doubt or any feedback to give, you can type. Okay, thank you. So all of you are doing MSc? I have talked to some of you, but some are new. So Shikha, I know. Shikha Divedi is new. Bonagiri Nikhil is, I know. Pushpita, I know. Okay, Kedar is doing job. Okay.
Ma'am, we will continue next week.
Yeah. Actually, yeah, today is the third week, and this session will go up to 10 or 12 week at least.
Okay, ma'am. Thank you.
So thank you so much for joining. You guys can leave.